All right, 8.7, rational exponents. Rational just means fraction. All right, so we're dealing with exponents that are fractions. We have two different notations. We have radical notation, we have exponential notation. We've talked about it before. Notation is just the way you write something. So if I have radical notation, that would look something like, so I've got a radical with an index of b and a radicand of x to the a power. Alright? If I wanted to put that in rational notation, rational exponent notation, what I'm going to do is I'm going to take the radicand, the base of the radicand, that's going to be my base over here, and I'm going to raise it to this exponent over this index. So it's going to be raised to the a over b. Alright, so what that would look like for us is if I have the square root of x, I have to know that there's an understood 2 for an index and an understood 1 for an exponent. That would be the same thing as x to the 1/2. Alright, so the exponent goes on top, the index goes on bottom. That will help us when it comes to multiplying certain radicals or reducing them. So let's see what it's going to look like. If I have something like, let's just change it to exponential form first. If I have the 8th root of x, and I want to rewrite that as a rational exponent, that would be x is my base, there's an understood 1 over 8. Same thing we did a second ago. Now let's look at, what if we have the 7th root of x squared y cubed, and it wants us to write it as a rational exponent. That would be x to the 2 over 7, y to the 3 over 7. Alright, that's as far as we can take that one. What if we have, where's the benefit come? What if we have the 6th root of 49? Alright, if there's a way that I could rewrite this, if this was a perfect 6th power, then great, it would reduce, but it's not. There's nothing I can multiply by itself 6 times and get 49. So what I'm going to do is I do recognize I can rewrite this as something with an exponent, right? This is the same thing as the 6th root of 49 is the same thing as 7 squared. Alright? Now I'm going to change it from radical notation to exponential notation. So I'm going to have 7 to the 2 over 6. 2 over 6 will reduce. That's the same thing as 7 to the 1/3. And now I could change that back to radical notation, and I get the cubed root of 7. Alright? So that's where the benefit comes, is this I can clean up by converting it to 7 squared. 49 is the same thing as 7 squared. Anytime I can change it, if that's a perfect square or a perfect cube, I need to be able to recognize that and understand that 49 is equal to 7 squared, which means I can interchange those two things. So whether it was 49, I changed it to 7 squared, changed it to rational exponent notation, reduced it, converted it back, and it cleaned it up a lot. The cube root of 7 would be your final answer there. What about the 4th root of 9a squared b to the 4th? Right? And all the directions say is simplify the radical expression. My first step is always, can I change anything to have an exponent? So 9 is the same thing as 3 squared, a squared, b to the 4th. All right, that's the same thing as 3 to the 2 over 4, a to the 2 over 4, b to the 4 over 4. All right, when I clean all that up, that's equal to 3 to the 1/2, a to the 1/2, b to the 1, b to the 1st. Here's where it gets a little bit tricky, but when I go to change this back to radical notation, both of these have the exact same exponent, which means they can go under one radical together. The 2 is my index on the outside. My 1 is the exponent. So I'm going to have 3a times b to the 1st, which is just b. Now, I would never leave an answer like this, because if you don't write it really neat, you can do something like this. And I'm going to think that that b is under your radical. All right, so what we want to do every time, when I wrote it here, I wrote it clearly separate with a dot in between showing that it's separate. I'm going to move that b to the front. That's going to be b times the square root of 3a. All right, this is always the proper notation when you have a factor that's not under a radical, is to move it to the front. That way you don't accidentally include it under the radical and miss points that you shouldn't miss. All right, so 1, 2, 3, 4, 5 steps to do every single step in order and to get where we want to go. So get another example. If I have the 4th root of x cubed times the square root of x. So just like on this example, they're not always going to tell you to convert it to a rational exponent and then back to a radical. You're just going to have to understand that's the only way we can do it. We can't multiply the 4th root times the square root and combine them. We can't use that product rule that allows us to bring them together because the indexes aren't the same. So because the indexes aren't the same, the only thing I can do is to try to make it look different so that I can work with it. So if I've got the 4th root of x to the 3rd, that's the same thing as x to the 3 over 4 times, this one is going to be x to the 1 over 2. Now here's where I got to remember my rules. When I multiply x times x, I add the exponents. Anytime I multiply variables, the bases are the same, I add the exponents. So this becomes x to the 3/4 plus 1/2. I add the exponents. I can't add them until I get a like denominator. The LCD between 4 and 2 is 4, so I got to multiply this by 2 and this by 2. And I'm going to get x to the 3/4 plus 2/4, which is equal to x to the 2 plus 3 is 5/4, which is equal to the the square root, the root, the radical. So which one goes on the outside? It's going to be the one on bottom, right? 4x to the 4th root of x to the 5th. The numerator always goes as the exponent, the denominator always goes as the index. All right. I'm going to look at another one because I know we can make it harder than it should be. If I have the 4th root of x cubed divided by the square root of x, again, I can't use the quotient rule. I can't bring them under one radical because the indexes are different. So what I need to do is change it to exponential notation. X to the 3 over 4 over x to the 1 over 2. Understood 1, understood 2. Anytime I have a base that's the same being divided, I subtract the exponents. So that's gonna be x to the 3/4 minus 1/2. Have to do the exact same thing, get a common denominator. So I get x to the 3/4 minus 2/4, which is x to the 1/2, which is the square root of x. Alright, so changing it to rational exponents, simplifying, adding or subtracting them, depending on whether you're multiplying or dividing. Anytime you multiply them, you're going to be adding the exponents. Anytime you divide, you're going to be subtracting the exponents, making sure that you get a common denominator in the process. Alright, so that'll get you through 8.7.